Well, good afternoon, everybody. I hope everyone has joined who said they would, and I really thank you for joining us today for this webinar, taking time out of your busy days. And today we're going to cover some fundamentals of product and quality testing, as seen through CHATILLON and Lloyd Instrument eyes. A few bits of admin to go through firstly. So just to make you aware, this webinar will be recorded. All participants are muted for the duration of the webinar. Please feel free to ask any questions you have via the chat function. Either I can answer them myself at the end, and we have other people on the call who will field those questions in the meantime. We will have a Q&A session at the end of the webinar, should we need to. And obviously, we will share these presentation slides via email and post this recording to the YouTube channel. So this is me, Gavin Hall. I'm product specialist with AMETEK STC. So I do a number of roles, but a little bit of tech support, a little bit of application support, some pre and post test sale work. I have a 35-year history in the test and service industry, and predominantly the last 16 years has been in the fields of product and materials test sector. So a brief agenda today. Why do we test? How AMETEK STC can help. Some considerations for successful testing. Then we'll look into an equipment overview of the CHATILLON force gauge and the TCM test stand. And we'll look at a few typical applications, some additional test options, and then obviously we'll throw open to any questions that maybe have. So why do we test? So predominantly any manufacturer of a supplier of a product, be it a final end use or component part within a larger solution, has a responsibility to prove the design criteria has been met and hopefully exceeded. Any safety elements of that product's design or its operation. The functionality or operation is as expected. And any lifespan and longevity periods of a product. So in product testing, generally in quality testing, failure rates can be measured as MTBF, mean time before failure. So if we look at this trend curve on the screen, we have a downward going number of product failures initially during the R&D and pre-production phase. And it's a critical part of a product's testing phase. Thorough and accurate testing should root out design errors and improve product specifications. And hopefully the trend is in a downward failure rate. Then we move into the manufacture and working life of a product. The testing during this phase is mainly checking the quality of build and the manufacture process. And the trend of the failure should hopefully flatten out for the working life. And then we move into the failure or service. So aging of product or period of use can result in sudden or gradual failure. Work done during the R&D phase can be fundamental in predicting this phase. And we will see that the trend of failure will obviously rise. So using a test machine and or analytical software can help identify the key performance in a product's design and manufacture. And then that data gathered can be fed back into calculations to determine the failure parameters. So from a thorough and repeated round of testing, collected data can be fed back into the manufacturing process and can help a company identify or improve critical design failures or lifespan of a product, any supplier quality issues of raw material or component elements, failures in the manufacturing process, improvements to that process of manufacture, continuous improvement, and quite importantly, cost savings for key process improvements where we know a requirement for rework action can be very expensive. It helps to define warranty periods of products and limitations of use, and then help to generate revenue for service cycles and service periods post-sale. So before any acquisition of equipment for testing function can be considered, the following points should be reviewed. Identify the requirements for testing a product, be it safety, performance, its lifespan, and fundamentally its costing. So what are the key measurements to be taken? Are there just operational limits? Is there some element of stress or fatigue in that product? Are the measurements analytical? So are they more involved in terms of its operation or its key performance? Or is it simply to simulate the operation of that product? So a clearly defined product specification from which performance outcomes and measured results can be referenced. Identify the possible forces, it sounds pretty obvious, but involved, and the size of the specimen. This obviously aids in the choice of test equipment and grips to hold the product. And ideally, there should be a produced test specification or test method. And that should come from hopefully the R&D criteria and the use of that product. What's it designed to be used for? So how do we identify testing requirements and results? From a defined test method. Now this can be an in-house product specification, as mentioned before, that highlights operational functions and identifies the test limits, speeds, and results required to successfully measure performance and quality of manufacture. It could also come from a test standard. So many organizations such as ASTM, ISO, TAPI, there are many more around the world. These tend to cover more generally raw materials, but can be referenced for use with products to help identify test and result parameters. So raw materials go into product materials, so there is a correlation there. But generally, in many cases, it's a combination of both to define a test method. So other questions, how will the test sample be held during a test? What type of fixture or grip is needed? So sometimes it helps to provide us or a supplier with a dimensional mechanical drawing. Let's physically see the dimensions required. Will it fit in the machine? Can we provide a grip to hold that sample? Reference to a test standard. Again, recommended fixtures or method of handling can sometimes be defined if it's a specialty product within that test standard. Or is it simply an actual or simulated sighting of that product? So is it sighted in another part? Is it part of a larger assembly or application? So it's tested in its true operational form. So defining test limits and results. So what's the expected outcome of testing a product? Is a product to be stressed? Usually it can be stressed to a fixed limit, a force, an extension, and by extension, a measurement of its own height, or for a period of time. Is the product tested past a limit of failure or an action point? So is a break detected or a peak registered? Or is there a physical change in the product's condition? And the product can be tested in its design form to check its functional operation. Expected recovery from a test. So is it a relaxation test, a recovery point from an action of testing it? Is it a long-term period of test, fatigue testing, to check the operational lifespan or its mean time before failure? What results are required? Results, I mean, are general in most machines, but they have to be defined obviously from the operational use of the machine. But from our particular machines, they're force or extension values, and these can be captured during or after a test. Test results can be referenced from a defined test specification, so an in-house specification, a test standard supplied, or a functional performance of a product. So if we know how a product is supposed to perform in its end use, then we can define results based upon that. So how can we help? How can AMETEK STC help? So we're an established global company with over 50 years of testing experience. The two brands you see in the top right-hand corner, CHATILLON Force Measurement and Lloyd's Materials Testing, some of the oldest within the AMETEK group, and we've been around a long period of time. So we have a lot of experience in this sector. So we make a range of product and materials test machines and analytical software. We specialize in analytical quality and performance testing of products. And we supply into many fields. Some of those are listed there, but they're not exhaustive. And many specialist areas too. So we have a team of dedicated sales engineers and application specialists. Hello, I'm one of them. To recommend and advise on equipment needs, test application requirements and methods. And we are backed by a global distributor network for sales and support. So as I say, we specialize in many product quality and production line testing solutions. A selection of our machines are shown below. So here we have the CHATILLON TCM test stand and DFG3 force gauge. We have the CHATILLON CS machine with a touchscreen tablet software. And we have our Lloyd Materials Testing LS machine and Next-Gen Plus software. For today's element and the particular applications we're going to look at, we're going to look at the CHATILLON TCM test stand and force gauge. And that's predominantly because it's mainly suited for a production test or a quality test environment. So an end of line testing within a small production facility. Users can get quick access. It's quite lightweight and portable, so it can be placed in a convenient position suited to the production environment or indeed a quality control lab. So the gauge can be used as a handheld solution only, but more fundamentally, when used in combination with the motorized TCM test stand, the application coverage is greatly expanded. And this solution is well suited for the product quality testing. So there we've got the force gauge handheld, and on the right hand side we can see it mounted to the TCM test stand. Just a very quick overview on the gauges. They come in two forms, so the DFE and the DFS. Key to note on the DFE is that there is no brake detection available within that gauge, and there's no control of the test stand directly. The test stand is manually controlled. And the DFS, slightly higher performance specs in most fields. Key is that it does have a brake detection function and it does control the TCM test stand. So the menu functions within the gauge are used to control the test stand. This saves time in programming and saves time in operation when using the machine. So the test settings for the machine itself are done within the gauge. There is a menu structure that's controlled via the functional keys below the display. And you can see we have ability to set particular force units, the polarity of the gauge, so the gauge can be in tension or compression. We have filters, so do we make the gauge more responsive? Do we make it less responsive? And these are important when we come to look at key points such as peak detection or quick action parts of a test. Then we can set the test parameters, the test results, peak analysis, load averaging, and brake for the DFS only. We have the ability to start and stop on conditions of the test stand. We also have the ability to save results, export results, and set result limits. And we can display a particular result. And we have control over the TCM with the DFS gauge itself. The test stand itself, so it has a front panel control. Once it's been configured with a DFS, the test stand can simply be started over and over again. So it makes for high volume testing, speedy testing, and simple use. So there's no need to set the direction of the gauge. It's all done within the configuration menus. And if auto return is done at the end, the machine will come back to the home position, ready for the next test. Just very briefly, some just typical examples of where this equipment is suited into the product and quality environment. So in the packaging industry particularly, so lids and caps, closures, bottles and canisters, so compression testing, oil seals and seams, so peel testing, anything in the packaging industry, and particularly maybe across the food sector as well. And then we have carton or box forming, crushing. And then in the medical industry, we specialize potentially in needle insertion, medical seals, so hot seals for keeping equipment sterilized, syringe glide force, so extracting a liquid from a syringe, and then blister packs, so pill packs. As you know, when pills come in forms, they can be peeled off to open the packaging. We can test for the forces required to do that. So we're going to look at a couple of typical applications. So in this, we have a cap pull-off. So we have a product that has a removable cap. The aim of this test is to capture the peak force required to remove that cap from the specimen. And the results could be required for application reasons or for safety reasons, manual handling reasons. There's a number of elements of people could hurt themselves if there's sharp edges or if there's any significant forces to remove such closures or caps. And typical industries would include something like medical, pharmaceutical, packaging, or cosmetic. So in the picture, you can see we have a generic bottom grip to hold the sample. It's got to be fit to hold the sample safely and securely. And then we have a more specialist button grip in the upper fixture to ensure a good connection with the bottle top being taken off. So here's an example of the gauge being programmed. We can see using the menu system, there is a test selection system, a test setup that is selected. And there are 5, this is a DFS gauge on screen. There are 5 within the DFS, so 5 individual test setups. We're setting a tension polarity. We're actually going to do a pull-off test, so the stand is going to move up. We're setting the direction to tension. The units are in newtons. We can set the test speed to the defined speed, and that could come from a particular standard, or it could come from a research and development requirement. We're setting auto return, have a start condition of none, and a stop condition of extension of 20 millimeters. So the extension that we're going to stop at is just enough, to obviously pull the sample off. We're expecting the sample to break, so the break will fire and stop the test, but we have a reserve limit of 20 millimeters should the test not detect the break or the sample fail during its test setup. And then we simply save the test and we're ready to go. So there's my colleague, the operator, fitting the zeroing the grip. He's fitting the sample, tightening the grip. And we have some residual load on there. That's fine. That's an action of doing up the grip. We tend to remove that during the test. And then once we've set up, we simply press play or the go button on the test stand, and you can see the test stand is now rising at the fixed speed. To the required limit, and we will read off the load at that point. Then take the fixture off and remove the sample, ready for the next test run. Okay, so now just quickly to get a TPL tension. So this test is designed to capture the average force and the peak force required to separate 2 laminated or bonded surfaces. So the result could be required for a product performance, its application, or its lifespan, its wear and tear. And again, typical industries include adhesives, tapes, packaging seals, medical seals, textile seams, or laminated seals. And these particular grips are bollard grips, but they're designed predominantly to self-tighten. So as the sample maybe thins out in the grips, we retain a firm hold on that sample for the duration of the test. Again, some of the common settings. So similarly, a tension test in the gauge, tension test in the TCM tand itself. We have a higher test speed here, and again that will be defined by a particular test standard or a paper for this product. So auto return is also set, so the gauge will return after the test. We have load averaging mode in this gauge. So when the gauge reaches a particular trigger force, it will start to self-analyze within the readings of the gauge and record the average force being measured while the sample is being pulled apart. We have a timeout. In this case, it's set to 29 seconds. I mean, that can be obviously altered to suit your product. And the test will stop at that time when it's been reached. In the background, we have break detection enabled. So if the specimen breaks early during the test, it will stop. And the idea of that is that the break can help you save time. So some samples may fail early. There could be a design error, could be a production error itself. It could just be an early failure in the sample. But importantly, the test will stop at the break point, but results are still valid to that point. We have no start condition, and we have a particular stop condition called after averaging. So as I say, it will either stop at the end of the timeout or if a break occurs, and then results are shown on the main gauge display. We can see load average as the result, and we have the ability to save those into the memory of the gauge. So let's look at the test running. So you can see the test is started and the delamination is occurring. You can see why it's called a T-peel. It's an inverted T rotated 90 degrees to the left, and the action of the sample is to peel the two substrates apart. The test will last the defined period of time, and at the end of the test, when we see it complete, we can see an average peel force of 97.48 newtons. So that's the average force required to separate those two samples. And then we have the ability to look at the other result, which is the peak value, and we can see that a peak of 124 newtons was taken to separate those two. And we can have a look at the results to make sure they've been stored. And lastly, just a typical application, again, a top load compression, so very common in looking at the peak forces or break forces by compressing a specimen to a fixed distance. And we're checking for a yield, so a drop in the load as the sample either gives way, cannot withstand the force any longer, or actually fails and breaks. So the act of this is simply commonly used for stacking multiple packaging or containers upon each other when being shipped or stored to see if they have the strength without a failure. And typical industries are the bottling industry, food and beverage, many liquid packaging containers. So it uses upper and lower compression platens, and the platens obviously must be of a surface area to cover the area of the specimen or more. Again, a number of setup functions. This time it's compression positive. The force units in newtons again, but this time we're going to set the test stand to go in compression, and we have a set speed of 60 millimeters per minute. We have a break detection, this time set to C break, so the gauge will actually actively look for a load drop in the compressive direction. And within the break method, we have a percentage break, so we set it to 90%. The gauge will detect when the live force reading drops below that value. We have a trigger value arbitrarily set to 9.8 newtons, but the gauge will not start to measure, and the brake detection will not be active until that point. And the ability for that is to avoid any load noise that could be caused by sample settling or grip settling on the sample, and which could cause obviously a false brake detection. The gauge won't start until a 1 Newton start condition is reached, and we're going to set the stop extension or stop condition to extension of 3 millimeters. So this time it's a secondary stop condition, as brake detection is the main test stop condition. But if the sample did not break, again to save time, we will only move to the set distance. And here we go. So we load the specimen to the machine and start. It's over very quickly. The machine moves down, sample compresses and gives way, and we have a result of 191 newtons. So that is the brake load or the top load of the test. So just some additional info on test options. We have some external transducers, force AFM and torque AQM. And the idea of these sensors is they can expand the gauge capability, so the measuring and application capability, particularly torque. So torque, we have obviously a rotational force rather than an axial force, and these can be used as handheld openings or closings of twist tops or particular fixtures that require a rotational action. And we have the ability to fix the AFM to the TCM test stand, and this expands the operational capacity, or it can increase the accuracy, because we could be going lower in force on an AFM than we have on the actual gauge. So we expand the capability and the measuring range of the machine. And we have additional software, Force Test 3. So we have the ability to create a database for a variety of test methods, products or test specimens. From a menu system, we can select a test method and a data source. We have the ability to configure individual test parameters. So many of these are mapped from within the gauge itself, the gauge menu. And we have an ability to define test results. Obviously, with the software, we have the ability to plot live force test data, force extension and time from the TCM and gauge. And that can be helpful when overlaying particular tests. You can look at trend analysis, you can look at individual results and do comparisons and get statistical information from this software. There's a powerful report designer within there, so you can create visual reports with the built-in designer, and we can also export the results in many formats, CSV, PDF, amongst a few. And it just again expands the range of the test equipment. Okay, that's all from me today. I hope that's been reasonably informative. If there are any questions, please feel free to ask away, and I will open the floor. Okay, so on individual questions, Gabriele, I will come back to you on that question particularly. If there's nothing else I can help with today, then I really appreciate you attending, and I thank you.